Let's look at section 8.4. Factor the following completely if possible. The most important factoring strategy is to ask, is there a GCF? In this case, I noticed the 36, 16, and 50 have a common divisor of 2. And if we look at the exponents, we have x to the 8th, x to the 4th, and x cubed. They have at least an x cubed term that can be factored out of each one. So now we'll ask 2x cubed times what gives us 36x to the 8th. That's got to be 18x to the 5th. 2x cubed times what will yield 16x to the 4th. That's going to be a negative 8x. And then finally, 2x cubed times what will give us 50x cubed. That's going to be a plus 25. And that completes our problem. This is completely factored. In the next example, I again ask myself, what's the GCF? Each of these terms do not have a common factor, so there is no GCF besides 1 in this case. So we're going to look at the next question. How many terms are there? Well, in this case, we have 4 terms, and to do 4 terms, you have to factor by grouping. Let's look at the first pair and the second pair. For the first pair, notice we have a common factor of x squared. And then we'll ask x squared times what gives us x cubed? This has to be x. X squared times what gives us 18x squared? This has to be 18. Plus, we can factor out a 7 from the second term. 7 times what gives us 7x? This must be an x. And 7 times 18 gives us 126. Notice each of these has a common factor of x minus 18, so I can factor that to the front, x minus 18, leaving us with an x squared plus 7. X squared plus 7, this part is not factorable, and x minus 18, that's not factorable, so that completes our problem. In the third example, I am going to ask myself, is there a GCF? Is there something I could take out of each and every single one of these terms? And in this case, there is. We can take out a 3 or factor a 3 from each of the terms. Let's put that to the front. And then ask 3 times what gives us 3t squared? 3 times what gives us 3t cubed? This has to be t cubed. 3 times what gives us 24t squared? This must be an 8t squared. And 3 times what gives us negative 21t? That's going to be a negative 7t here. And t times what gives us 168. And so 3 times 56 gives us 168. And we took out the GCF. The next step is to ask how many terms we have. How many terms are there? In this case, we have 4 terms now. And so we can factor out the common factor for each pair. Put the 3 in the front. T cubed and t squared have a common factor of t squared, so we'll factor that out to the front, leaving us with t minus 8. For the second pair, we have a common factor of negative 7. I'm going to take out a negative 7 because that will leave us a factor of t minus 8. If I chose to take out a positive 7, the factorization doesn't work because we need these two to be the same. So we'll factor again now the t minus 8 from each of these pairs, and that leaves me with a t squared minus 7. And that is it. We have completely factored our expression. In the next example, again, I ask, is there a GCF? And in this case, we have a 2. I can factor out a 2 from each of the terms. Take that out to the front. 2 times what gives us 2x squared? That's an x squared. 2 times what gives us negative 8x? That's negative 4x. 2 times what gives us a negative 64? That must be a negative 32. Now we look at the number of terms. And in this case, we have 3 terms with a leading coefficient here of a 1 in front of the x. So I'm going to use the diamond method. We'll put the negative 32 on top and the negative 4 on the bottom. What two numbers multiplies to get negative 32 but add up to get a negative 4? That's going to be negative 8 and positive 4. It multiplies to get the top number and adds to get the bottom number. This factors as 2 times x minus 8 times x plus 4. And that completes the problem. In this example, I ask myself, is there a GCF besides a 1? And in this case, we don't have a GCF besides a 1. So we'll look at the number of terms. Notice that we have 3 terms, so this is the AC method. This is the AC method because we have a leading coefficient besides a 1, so we'll take the first term and multiply it with the last term. 2 times 24, that's going to be the number on the top. 2 times 24 is 48, and the number on the bottom is 19. We'll have to find 2 numbers that multiplies to get 48, but add up to get 19. So I'll make a list. 1 times 48, that doesn't work. 2 times 24 doesn't work. Let's try 3 times 16. That one looks like it works. 3 and 16 are our 2 numbers. And so we can now factor this by splitting the middle. I'll copy the first term and copy the last term here in the back. But we're going to split the middle as 2 terms. This is going to be split as 2x squared plus 3x. This 3 is why we put a 3x. And 16x plus 24. Notice the 3x plus the 16x adds up to get 19x. So what we did is we changed a polynomial with 3 terms into 4 terms. And the reason we do that is now we could use factor by grouping. The first pair has a common factor of x, leaving us with a 2x plus 3. The second pair has a common factor of 8, leaving us again with 2x plus 3 as the remaining factor. Since these two are the same, I know I did it right. I can factor out 2x plus 3, leaving me with an x plus 8. And now this problem is factored completely. In this example, we're going to use a formula called the difference of squares. Recall, the difference of squares is a minus b times a plus b. In order to do this, I'm going to rewrite it as something squared minus another something squared. Let's rewrite 16b squared as 4b squared, and that's going to give us 16b squared back. And to make a 9, we need to square 3. So this 3 squared gives us 9. So from the first line to the second line, there's no change. We just rewrote the problem. And the reason we wrote the problem is this is now our a in the formula, and this 3 is now the b in the formula. And so we can just plug it in. This is now factored as 4b minus 3 and 4b plus 3. This is again using the difference of squares formula. In this example, it is of the form a squared plus b squared, but wait! If you can rewrite something in the form of a squared plus b squared form, this thing is prime. You cannot factor it. Sometimes we can't factor a polynomial, and so this is our answer. It is prime. You cannot factor this. In this example, I will ask, is there a GCF? And in this case, we don't have a GCF besides a 1. So we can now look at a different strategy. Notice there's a cubic term here. So I'm guessing this is the sum of cubes. And the formula for that is a plus b times a squared minus ab plus b squared. Using this formula, we should be able to factor the sum of cubes. Rewrite it as something cubed plus something cubed, 27x cubed. How do we make that back? Well, we need a 3x, and once we cube that, we get 27x cubed. How do we make a 125 back? We need a 5. 5 cubed is 125. And so now this is my a, and this is my b. So let's rewrite our factored form now. We have to say a, which is 3x, plus b, which is 5. And then we'll put another parentheses. And a squared would be 3x squared minus 3x times 5. That's a times b for you, 3x times 5. And then for the last part, we need to do a b squared, which is plus b, which is 5 squared, and then we can simplify. This can be rewritten as 3x plus 5 times 3x squared gives me 9x squared. Negative 3x times 5 is negative 15x. And for the last part, 5 squared, that's 25. We are done with the problem using the sum of cubes. In the next following examples, we will be solving equations. First step is to see if we can factor them. And in this case, I can factor this using the diamond method. Negative 36 on top, 5 on the bottom. The two numbers are 9 and 4. We have a negative 4. And so this factors as x plus 9 times x minus 4 is equal to 0. Now, according to the zero factor property, if you have two numbers that multiplies to get 0, you can say that one of them is 0 or the other is 0. Or it could be both being 0. So for this example, we can set x plus 9 being equal to 0. Or we have x minus 4 equals 0. That's the only way we will get a 0 if we multiply two numbers. For the first one, I could subtract 9 to both sides, and x equals negative 9 is our first solution. For the second one, we'll add 4 to both sides, and so x equals positive 4 is our second solution. If you're not sure, you can check your work, plug it into the original function, and make sure it does equal 0. For this problem, I will begin by factoring, and notice we do have a GCF, so let's factor out the common factor. It looks like the common factor is 4. Take the 4 into the front, and so 4, when factored out, leaves us with x squared minus 11x plus 18. Again, if you're not sure, you can distribute the 4, making sure the product is the original equation. Alright, now we can get rid of that 4. We can divide both sides by 4, and notice the 4 is now divided out, leaving me with x squared minus 11x plus 18 equals 0. We have three terms. I'm going to use the diamond method. Negative 18 on top, negative 11 on the bottom. What two numbers multiplies to get negative 18 but add up to get negative 11? We have negative 2 and negative 9 works. This factors as x minus 2 times x minus 9 equals to 0. And so I could set each one of these factors equal to 0 now and solve for x. For the first expression, let's add 2 to both sides. And that leaves us with x equals positive 2. That's our first solution. For our next problem, let's add 9 to both sides. That leaves us with x equals 9. That's our second solution. And feel free to check our work, plugging it into the original equation and making sure you get 0 out of that expression. Before we start the problem, always rewrite your equation in the form of ax squared plus bx plus c equals to 0. Once it's in this nice standard form, then we will be able to factor. So I'll start by subtracting 4x to both sides. That gives me x squared plus 7x is equal to negative 6. Then I could add 6 to both sides, again to make the right side 0. And so this is x squared plus 7x plus 6. Since it's 3 terms, I can use the diamond method to factor this. And the two numbers are 1 and 6. 1 times 6 gives us 6, and 1 plus 6 gives us 7. So it factors as x plus 1 times x plus 6, and that's equal to 0. Since both of these factors are multiplied to give us 0, one of them could be 0, or it could be the other being equal to 0. And so I could solve each one separately now. For the first one, we're going to subtract 1 to both sides. That leaves us with x equals negative 1. For the second one, we subtract 6 to both sides, and x equals negative 6 is our second solution. Feel free to check your answer, plug it into the original equation, and you should get that they are equal on both sides. For this problem, I want to start by finding the LCD of the denominator. In this case, we have denominator 3, 3, and this one has an invisible 1 as the denominator, so the LCD is 3. Multiply every single term by 3 to get rid of those fractions. And again, we're going to multiply every single term by 3 on both sides of the equation. Every single term is multiplied by 3. 3 times 4/3 x squared, that reduces to 4x squared. 3 times 14x over 3 is just 14x. 3 times 2 gives me 6. And this is equal to 0. And it's in that standard form that I want. Now I can factor. Notice they have a common factor of 2. Let's factor out the 2. And so that leaves me with 2x squared plus 2 times 7x gives us 14x. 2 times 3 gives us 6. And so this is factored. I can get rid of the 2 by dividing both sides by 2 just to simplify our equation. This leaves us with 2x squared plus 7x plus 3 equals 0. Notice we have 3 terms, but there's a leading coefficient. Since there's a leading coefficient, we're going to use the AC method, taking the first term times the last term. That's a 6 on top and a 7 on the bottom. What two numbers multiply to get 6 but add up to 7? That's 1 and 6. Now be careful here, you're going to have to split the middle since we are dealing with a leading coefficient. So I'll split the middle as these two numbers, 1x and 6x. 1x plus 6x gives us 7x, so we did not alter the equation. Notice that we have 4 terms, so we're going to do factor by grouping. So I can factor out an x here, leaving me with 2x plus 1. For the second term, let's factor out a 3, leaving us again with 2x plus 1, which means we're factoring it correctly. Since they're both the same, we can factor that out to the front, leaving us with a remainder of x plus 3. Since we have two numbers multiplied to give us 0, we can set each one separately equal to 0 and solve. For the first one, we could subtract 1 to both sides. 2x equals negative 1. Divide both sides by 2, and so x equals negative 1/2. That's our first solution. And for the other one, we can subtract 3 to both sides, and x equals negative 3. That's our second solution. For the next question, it's really important that you know how to figure out the LCD. To figure out what the LCD is, I usually just take all of the pieces of the denominator. So in this case, I have a denominator with x plus 2 and x plus 6. This is going to be my LCD. It has to be divisible by all of the denominators, so we need an x plus 2 and an x plus 6. To get rid of the fractions, we'll multiply x plus 2 times x plus 6 to every single term. That means I'll need to multiply it to x plus 1 divided by x plus 2, and that's equal to our LCD again, which is x plus 2 times x plus 6 times the right side, which is 6 divided by x plus 6. Now the reason we're doing this is notice that the x plus 2 and the x plus 2 divide out. The x plus 6 and the x plus 6 divide out. This leaves me with x plus 6 times x plus 1, and that's equal to x plus 2 times 6. To solve this, we need to multiply this out. I'll multiply x times x, which is x squared. X times 1 is 1x. 6 times x is 6x. 6 times 1 is 6. On the right, we could distribute the 6. This is 6x plus 12. Let's collect like terms. We have x squared plus these two make 7x. And we'll drop down the plus 6. On the right, I'll just copy 6x plus 12. Again, to solve these problems, you want to rewrite it in that nice standard form, equal to 0. So we'll start by subtracting 6x to both sides. And let's also subtract 12 to both sides. This leaves us with x squared plus x minus 6 equals 0. It's a 3-term polynomial here, so let's factor using the diamond method. There's an invisible 1 in front of that x. So what two numbers multiplies to get negative 6 but add up to get 1? It's going to be a 2 and a 3, but it's a negative 2. That's the correct two numbers. Negative 2 times 3 is negative 6, and it does add up to get 1. There is no leading coefficient besides a 1, so this is easy to factor. It's x minus 2 times x plus 3 equals to 0. I can set each one equal to 0 now and solve. For the first case, we have x equals 2 as one solution, potential solution. And for the other case, if we subtract 3 to both sides, we get x equals negative 3. So this is our second potential solution. The reason I said these are potential solutions is we have to check to make sure they actually work. You have to be careful when you check your work that you look at the denominators carefully. The first solution was 2. If I plug a 2 into the denominators, we do not get a 0. So 2 is a good solution. 2 is a great solution. It does not cause the denominator to be 0. Let's check negative 3. If I plug in a negative 3 into the x for the denominators, you will realize that it's also good because the denominator is not 0. So, negative 3 is also a good solution. You need to check that there is no 0 in the denominator. We want to make sure that there is no 0 in the denominator, because if there was a 0 in the denominator, it would be undefined. you cannot divide by 0. So again, check to make sure there's no 0 in the denominator of our original equation. Let's start this problem now by looking for that LCD. I want to take the x minus 3 because I need to be divisible by x minus 3. I want to take that x plus 5. Again, I want to be divisible by x plus 5. If you look, we have x minus 3 and x plus 5 here. I don't need those terms because we already have x minus 3 and x plus 5 in our LCD. To do this problem, we'll take x minus 3, x plus 5, and we'll multiply that to each and every single one of our terms. Again, x minus 3, x plus 5 is going to be multiplied to each and every single one of our terms. And so it's x minus 3, x plus 5 times x over x minus 3. That's the first term. It's x minus 3 times x plus 5 times the second term now. And for the very last side here, we have 8x over x minus 3, x plus 5. And the point of using the LCD is so we can get rid of all of these fractions. So notice the x minus 3, they divide out. The x plus 5 divides out. And on the right side, all of them divide out except the 8x. So this leaves us with x plus 5 times x plus x minus 3 times 4, and that's equal to 8x. We can distribute the x now. That's x squared plus 5x. And I can distribute the 4 here on this side. That's 4x minus 12 equal to 8x. And so I can collect like terms. This is x squared plus 9x minus 12 equals 8x. Let's subtract 8x to both sides. And so x squared plus x minus 12 is now equal to 0. That nice standard form that I was looking for. This factors using the diamond method. This is going to be 3 and 4. It's a negative 3. We have an x minus 3 and an x plus 4 as our factors. And so we can set each one of these equal to 0 to solve for x. And you can see that the first solution is a positive 3, potential first solution. And for the other one, we have a potential solution of negative 4. So we need to check a positive 3 and a negative 4 to ensure that the denominator does not become 0. So let's check. If I plug in a 4, there's no problems. There's no way that the denominator is 0. But if I plug in a 3, we have a problem. The denominator here, 3 minus 3, would get a 0, and that's not possible. You cannot divide by 0. That's undefined. So we'll toss out positive 3. That's known as an extraneous solution. It's a solution that doesn't work. And so we only have one answer, and that's x equals negative 4. Be careful, check for those extraneous solutions when you're dealing with an equation that has denominators. Before I start this problem, I am going to factor the bottom right. So let's factor that. And that factors as the following. It factors as x plus 1 times x minus 5. You could check that with the diamond method. And those are our two numbers, 1 and negative 5. From here, we can multiply each and every single one of our terms with the LCD. What's the LCD? Well, the LCD is x plus 1, x minus 5. That's what we need to be divisible by every single one of the denominators. So let's multiply x plus 1, x minus 5 times the first term, x plus 1, x minus 5 times the second term, and again x plus 1 and x minus 5 times the third term. These will cancel out, and all of these on the denominator here cancels out, leaving me with x minus 5 times 3 plus x plus 1 times 1 equals 2x minus 4. Let's distribute that 3 now to the terms and the 1 here. So we have 3x minus 15 plus x plus 1 equals 2x minus 4. Let's collect like terms. 3x and x is 4x. Negative 15 and 1, that's negative 14, equals 2x minus 4. Now, typically we want to rewrite it as ax squared plus bx plus c equal to 0 form if there is a power of 2. But notice there's no power of 2. This is just a standard solving equation. So I'll just get the x on one side by subtracting 2x. And we'll also add 14 to both sides to get that to the other side. This simplifies to 2x equals 10. And now we could divide both sides by 2, and x equals 5. This is, again, a potential solution. We have to check our work. We have to plug it into the original equation, x equals 5. The denominator here for when x equals 5 is 0. That means x equals 5 is not a good solution. It's an extraneous solution. But that was our only option. And since it didn't work, that means there is no solution. So our answer here is no solution because x equals 5 was an extraneous solution. It didn't work.